Today we're going to introduce the Fourier Transform. The Fourier Transform is very much like a Laplace transform, which you may have seen before, but it is more general, a little more complicated, but because of that, it's also more powerful. To understand this video, you need to know a little bit about complex variables and some integration methods and simply what a PDE is. Okay, so let's talk conceptually first. Imagine we have a function, little f, of x and t, where x is space and t is time, and f is some physical quantity in the real world, maybe the concentration of a contaminant in some medium. Now, we are going to transform this function, little f, into a different but related function, big F, which is a function of k and t, where k here is a wave number. And if you don't know what that means, it's essentially a length scale in the problem, but it's actually an inverse length scale. And by that I mean, as k gets bigger, the length scale actually gets smaller. So here's an example. If we had a function f of x, which looked something like this, there are several length scales in this problem. Here's one, for example. Here's another smaller one here. Oops. And in fact, there are many. So you can think of little f and big F as just two different ways of describing the same data. Little f measures the magnitude for a point in space, x, including contributions from every wavelength, every k. Big F, on the other hand, measures the magnitude for a certain wavelength, k, including contributions from every point x in space. Okay, so before we do any more, let's define the Fourier transform mathematically. So, we often use a script f, like this, acting on our function little f. So notice that the Fourier transform is like a function on a function. And that you've seen, sometimes we write it as big F of k and t. The definition, and there are actually several, but this is the one I find easiest to remember. 1 over square root of 2 pi times an improper integral from minus to positive infinity of e to the I kx times our function, little f, integrated with respect to x. And notice two things. First, t is not affected in the integral. Only x is affected. And the second thing is that we have introduced a complex variable here. While little f is usually a real function because it represents a quantity in the physical world, we have introduced complex variables through the imaginary number I here. So there's a cost of doing this transform, and that is that we've introduced complex variables. That makes it a little more difficult. However, we do it because there is a clear and larger benefit, and that is that the operations we will have to perform in k space are easier than if we tried to perform them in x space. And we'll come back to that. Now there's one other definition, which is just the inverse transform. It's how we get back to little f. So we write it often as the inverse script f, now performed on f of k and t. And it has a similar formula, but with a slight difference. 1 over square root of 2 pi, again an improper integral, of e now to the minus I kx, integrated with respect to k, multiplied by big F of k and t, integrated with respect to k. Now, how do we use these definitions? Well, imagine we have some kind of problem in x space, in real physical space. Maybe it's a partial differential equation, or PDE. What we're going to do is transform, using the Fourier transform, into k space. Then in k space, we're going to solve it. And we do it there, again, because it's easier to do it there. And then we use the inverse Fourier transform, which we just defined, I'll write it that way, to get our solution. Now, there's a wonderful analogy to making clothes. So when you're going to make a piece of clothing, say a dress, you turn the pieces inside out and then sew them together with them inside out, and then you turn them back right side out. It's much easier to do that, it turns out, than to try to sew the pieces together with them right side out. You'd have to put your hands inside the dress. You wouldn't be able to see what you were doing. It'd be much more difficult. And so you take the trouble to go through the turning inside out process and then turning it back right side out. It's the exact same thing we're doing here, except it's in mathematical abstract space. Now, we keep talking about the operations being easier. What do we mean? Well, there's an example that's fairly easy to show. It's about taking the Fourier transform of a function that's a derivative. So, imagine we have a function u, and we want to take the Fourier transform of u prime. Now, I'm using a shorthand here. Really, I should have written du dx, because as you see, u is a function of x and t. I didn't write that very clearly. Let's rewrite that. U. There we go. U is really a function of x and t, so I should have written du dx, but for speed and space, I'm just going to write it as u prime and leave off the x's and t's. All right, now what does this equal? Well, let's write it down according to the definition. 1 over square root of 2 pi, our improper integral, e to the I kx times u prime dx. Well, this, I hope, screams out at you for a method of integration called integration by parts, because here you can see we have a function f and a function g prime. And let's remember what integration by parts, the rule of that looks like. So I'm going to write it down here in orange. So if you have an integral of f g prime for those two functions, f and g, integrated over limits a and b, it's equal to two pieces, f times g at the limits, minus sort of the opposite integral. Instead of fg prime, we have f prime g dx. So let's use that definition in our integral here. So rewriting it, we have the Fourier transform of u prime is equal to, the first term is 1 over root 2 pi, and now we have to write down f and g evaluated at the limits. So f is just e to the I kx, and g, well, since we have g prime as u prime, g is just u. So we evaluate that at the two limits. And then the second piece is minus our, 1 over root 2 pi times our improper integral again of, now f prime, well, if f is e to the I kx, f prime is ik times e to the I kx, and g again is just u dx. Now, we can simplify both terms here. This term, the first term, we're going to assume goes to 0 because we want u, our physical quantity, to disappear at infinity because we just assume it's bounded. So we neglect that term. The second term, this should be calling out to you, it's just the Fourier transform of u here. So we have the Fourier transform of u prime is just minus ik times the Fourier transform of u. Let's write that down. The Fourier transform of u prime equals minus ik times the Fourier transform of u. Well, look at that. We have just gone from differentiation, u prime, to multiplication. We just have to multiply by minus ik. This is the power of the Fourier transform. It makes the operations much easier. Now you can also see we could keep going here. We could find the Fourier transform of u double prime and u triple prime, etc. You can keep going. It's not difficult. And once you do this, it allows you to solve rather complicated problems fairly quickly. So we don't have time here, but next time we should use the Fourier transform to solve a PDE. So for example, here's a partial differential equation, a common one. U partial with respect to t equals a, some constant, times uxx, the second derivative of u with respect to x. This is called the diffusion equation. Some people call it the heat equation. And you can apply Fourier transforms directly to this and solve it with just a few integrations. Thanks for listening.